For each X-ray, you will derive just 10 data points. And then what happens is in the actual machine learning classification, you will use this derived data from the original image to feed into a machine learning classification algorithm. So what we need to look at when we're talking about being able to apply a machine learning technique on breast cancer X-rays is that you take each X-ray, get an expert doctor, let him compute these 10 columns, and then you create one row of data. And then you say, okay, this is cancerous. In some case, it may not be cancerous. You collect thousands of such rows, and then you feed it to a machine learning program, and then the machine learning program will come up with, okay, the formula for connecting input data to cancerous. But when you get a new cancer or not cancer X-ray, you convert them to this kind of a input variables and then predict whether it has cancer or not. So what is happening if you talk about simple machine learning as applied to this kind of a scenario? So the basic idea, what happens is we talk about conventional machine learning, which we saw, requiring handcrafted features. Handcrafted features means artificially derived input columns like this. You saw, right, how each doctor has to sit and write this or derive these columns for getting data for breast cancer classification. Same thing you can do for other domains. So what happens is, in machine learning, when you work with images like this, it will require artificial columns called features in the input to run a classification. And this is a very costly affair. And such handcrafted features are time consuming because a doctor has to sit and convert a typical image of X-ray into these values. Sometimes they do not scale because you may not have enough doctors or experts who can convert the X-rays into this kind of arguments. And they're expensive because you require a lot of effort. So what happens in conventional machine learning is whenever you want to work with images or text, you have to convert the original raw data into such artificial columns or features in the input data. Then you run your classification or regression or clustering or whatever machine learning you want to do. So let's take another example. Let's say we're talking about image of this car. So we can have columns like what's the color of the car? Is it a racing car? Is it a diesel car? Is it a petrol car? So these are different artificial features you can add. So what happens in machine learning is you have to constantly identify different columns of data which require to be prepared for approximating the data in the image before you apply the actual image classification. Like you saw here, it's a classification. Output is malignant or benign. But what is the input? Input is some derived data which doctors can derive from seeing an actual image of X-ray. And then you get this kind of data points, and then you start deriving the actual verification whether the model is going to be able to predict breast cancer or not. But as I said, this is time consuming. It requires expertise. Sometimes it may not be possible to get experts to do this kind of artificially creating columns for machine learning, etc. So what deep learning does is it allows us to cancel this artificial feature engineering step of the artificial columns. And what it can do is it can take directly input data and do corresponding machine learning task like classification. And that is the biggest advantage of machine learning. How it does? It does by automatically learning a hierarchy of features. Automatically from raw data. Could be image, could be text, sound, or large structured data, etc. So the concept here is that unlike here where we had all 10 columns were artificially derived, here you derive a hierarchy of features, call them as variables. But you don't need an expert to come and tell that this is the variable I'll use, like color of car, or maybe this radius of this, or perimeter of this. I don't care about that. But what deep learning does is it takes a raw image, converts it into its own internal representation of features, which can directly feed into classification. So what happens in deep learning? You don't need these 10 features. All you need is you just get the raw X-ray and label it. Does it have malignant cancer or does it not have cancer? You get thousands of images, label it, and then feed it to deep learning. It will automatically learn the pattern inside by understanding a set of features it automatically derives. And then when a new image X-ray is given to the deep learning model, it automatically tell you whether it has cancer or not. So the classifier is not built by machine learning of derived features from image, but working on directly the features from the image. That's exactly what deep learning does. So let's take an example. The hierarchy of representation is something automatically extracted by deep learning. And that is why deep learning is so powerful. All the examples you saw in the video, right? Images of constellations or images related to driverless cars or understanding each generation of music, all of them work with deep learning. And the way they work with is they take the raw data. Let's say this is the image. Let's take the left one. Let us say we have the image here, which is of a car, right? Now, from the car, at the lowermost level from the image, they extract small edges. This edge, this edge, this edge, this edge, this edge. From the edge, they'll try to derive some parts, like is this a headlight? Is this a steering wheel? Is this a wheel? Like that, it'll derive the next. And collection of these parts, they'll say, okay, this is this model of the car. This is most likely the car of this kind of a pattern. So what happens is, as you go up, you build higher level features from low level features. And all of these are generated automatically. This hierarchy of features, starting from edges on the image, edges going to parts of the car, parts of the car going to the whole car. Let's take another example. Let's say we have a writing here in a diagram called meeting at 4 p.m. At the lowermost level, we have edges. In the image, you see, this is what the edges is detecting. From the edges, it is deriving strokes. From the strokes, it is deriving actual characters. It could be 4, question mark, P, M. From combining characters, it will combine some meaning. Like, let's say, is there a time? Is it because 4 p.m.? Then combining multiple concepts, it says there is something called as meeting time. Let me give you one more example. Let's say we have a whole bunch of faces here, human faces. So we'll just see at the lowermost level edges. From the edges, you'll come to here. There is this teeth, there is nose, there is eyes, etc. From the combining them, you get a unique face. So in general, in deep learning, you automatically learn a hierarchy of features between input and the final class. Input could be text, speech, large data, video, image. And final layer is usually something related to the output. Is it a class of the input or it could be a value? And intermediate layers are all automatically generated. And each subsequent layer combines features from the lower level, like all edges together forms parts together form the face or parts together form the cardboard. So what you need to understand is in doing this automatic extraction, you are avoiding this creation of artificial columns which are representing the original image. So what is the advantage of deep learning? You can directly work with image and do classification. You don't need an intermediate expert to come and give you gyan of what features to be done. And that's exactly what happens in deep learning. So as I said, we started with AI as intelligence expected machines. In that, machine learning, as you know, is a part of AI where we talk about automatically learning patterns from data. And as you give more and more data, it gives better. And within that machine learning type, whether it's classification or regression, etc., deep learning is that subset where you automatically extract features from raw data and make the process possible. So at this point, I want to stop and ask anyone has any questions, because this, what I've taught you, is very fundamental as to why today deep learning is successful. Any questions? Any questions on why deep learning is today so popular as compared to machine learning? So as you can see, what it does is it avoids the concept of feature engineering. Earlier, if you look at this example, which we had, right? If you had looked at the example of the breast cancer, you needed artificial variables as inputs to provide to the classification. Now in the deep learning world, what are you doing? You're trying to just directly jump from image to classification. You give tons of breast cancer x-rays and you pass it to the deep learning model. It will learn the features automatically. What's the feature set? It will be like a hierarchy, right? You saw the hierarchy which we said. Hierarchy is like there is a lowermost hierarchy, then next, like that. There's an automated hierarchy. So any questions on this concept, why deep learning is so powerful and why all the examples we saw on AI are mainly based on deep learning? So deep learning has enabled us to work with unstructured data like images, text, audio, video as easily possible as compared to conventional machine learning where you had to go through it indirectly by converting them to columns before you can do actual machine learning. Any questions before we proceed on why deep learning is important? Yeah, the reason why deep learning works with higher data is that if you look at the progress of how these layers are formed, these hierarchy layers are formed, they require a kind of structure known as neural network where there are lots of weights connecting each layer to the next. And if they have to be stabilized and not inaccurate, you need lots and lots of data for images or input data for getting a stable network which will not change with every new data. So that's why deep learning works in terms of avoiding feature engineering, but it is also very data hungry. It's also based on the idea that because you have lots and lots of data which you can feed, it will be enabling the process of creation of such automated hierarchy of features. Any other question? Can DL represent resulting in cognitive systems so that what the complexity of DL? Oh, complexity. If you want to look at theoretical complexity, it is p-space. Don't worry about it. It'll be p-space complete. It's quite complex. It's not polynomial. It's not exponential. It's not even NP. It's beyond NP. DL surprising cognitive systems, I don't know. I think in terms of the cognitive systems surpassing human intelligence, I think it's a debate which is not worth it, because today, whatever said and done, we are still at a very, very first preliminary stages of AI. Because AI in the worst form is called narrow intelligence. And today we are in the form of AI, which is the worst. Because what we are seeing is a narrow AI or weak AI, also known as weak AI, because what is today's AI? It can detect a cancer, but what are we doing? We're sending thousands of images with labels. Is it cancerous or not? Then it is going and detecting a particular cancer, breast cancer is present or not. Same way, if you're teaching a car to drive around in California with California roads after images of all are obtained. But now take the engine which you have detected used for breast cancer. Can you go and make it go and detect lung cancer? No, you cannot. Same way, let us say you have a program for driverless car trained on California roads. You go and ask it to drive in London, it will fail. But take a human will probably be, even though you have learned driving in India, it's right hand drive. But when you go to US left hand drive, it does not take you more than 1 or 2 hours to get acclimatized and start driving in US. So human intelligence is far, far more dynamically configurable without need for retraining. Whereas today's successful AI systems, all the ones in the video we saw, are examples of deep learning and specialized machine learning based AI, which are based on feeding tons and tons of data. Then they extract the patterns from there, which cannot again scale once you go into a new domain. So it is actually the worst form of AI, or the easiest form of AI, called narrow AI. The real AI is yet to come. It will take 30, 40, 50 years maybe to mimic human intelligence. So this question, I feel, is more for people who don't understand AI. They try to create fear. Because ultimately, if any of you remember the movie Robot, the red button was always in the hands of the doctor, right? The scientist will always control the robot, but no matter how much you can do. Think about a program you written in causing infinite loop in your computer. You always have the control C to bring that loop back to control back to you. So it is important for you to understand that whenever you're trying to create a scenario where you feel that it is better than humans always have the control. So this question, I strongly say, it is not ever possible to, it's not ever possible to create human level intelligence. So the next question which I have is, which is better, DL with TensorFlow or DL with Python? TensorFlow is implemented in Python. I will show an example today in the CNN class with TensorFlow. So TensorFlow is better for different DL architectures. Python is very limited. They only have basic MLP. Can we use deep learning in wireless communication? Yes. Today, there is a lot of work happening on using of deep learning based optimization, etc. in 5G, because 5G has lots and lots of configuration parameters. So in fact, that's a huge research area, using machine learning and deep learning in 5G. People who are in networking, I suggest you take up projects around use of AI, ML, DL in 5G networks, because of huge configuration parameters. It's not possible to do it by human to configure all of them to find optimal paths. So you need to use. How to analyze accuracy of DL? There are standard metrics. See, DL does not change the problem. Ultimately, you will use the DL for classification only, right? So whatever metric you will do for classification will be used. If you're using DL for regression, you will use mean square error. If you're using classification, you will use accuracy. So it doesn't make much sense. How much time it takes to train deep neural network? It depends on how many examples you have. It's minimum you require hundreds of examples, but the more examples you have, and also it's a function of what architecture you're using. Are you using a CPU architecture or a GPU architecture? If you're using a GPU, which is a parallel architecture, it takes 1/100th of the time of typical CPU. So it depends on what architecture you're using. In terms of deep learning, is cognition machine learning, is memory, and can we understand in this way? You cannot. Today, deep learning is just, I can say, dumb pattern recognition. There's nothing more. It's all about tons of data you give, you extract the hierarchy of layers from there. That's all it is. Okay. So what you need to understand is DL is machine learning. So there's no separate concept of metrics for deep learning. So in this case, when I said I want to do the breast cancer example, if I take the metric for this, it will still be based on accuracy because it's a classification. So DL does not change machine learning metrics. DL does machine learning. So that's one thing I wanted to clearly clarify, that we don't get out of machine learning domain, even though you're deep learning. But what you do get out from this junk of having to write artificial columns of variables derived from experts for each image. Instead, you can directly image into classification. Okay. So I hope the concepts of deep learning are clear, why, where it is used. It's ultimately going to be extremely powerful because of this way by which. So it is because of the deep learning being able to work on unstructured data like images, directly extracting features. Otherwise, the feature engineering is a very big pain. So the question we have is, which one is better, DL with features or DL without features? DL does not have features. Well, the moment you say deep learning, you don't have features. Let me tell you, you don't have concept of features. The moment you say you're working on your own features, it becomes practically conventional machine learning. So you need to be very clear about, are you going to give raw data or are you going to create your own features and feed it? So the point which I also wanted to mention is, in context of deep learning, there is one thing which is very important for us to understand in terms of accuracy. Let us say you talk about, this is amount of data and this is suppose accuracy. What happens is, in conventional machine learning, you kind of reach peak of accuracy after a certain level. Whereas with deep learning, the more data you give, the higher accuracies you can achieve. So that is the basic advantage of DL, that it basically helps you in extracting a larger accuracy if you have more data. Whereas conventional ML with handcrafted features may stagnate at certain level, whereas DL has the potential to take the accuracies to higher level with more data. But the actual reason why DL may be not required in all cases is, it may not be that all machine learning problems require you to work on large data. You may have very small data. Then you may be better off doing some linear regression or logistic regression as compared to deep learning. Okay. So now, I hope this concept was clear. This has to be clear for all of you, because people talk about a lot of deep learning, neural networks, everything. But what they don't understand is, why is this so powerful? Why is this so popular? The reason why it's powerful is, do you use existing training network? We'll come to that. See, ultimately, there's no concept of stopping. It's up to you where you want to stop. What is the accuracy which is good enough for you? So there's no concept of existing network being good or not. It only depends on what is the limit of accuracy you are comfortable with. Are you happy with 99%? That's fine. Otherwise, you go back and retrain and do more loops. Is it right that we cannot understand AI without machine learning? Absolutely wrong. AI is a large umbrella. AI is a large umbrella of technologies which mimic human intelligence. Whereas machine learning is one part of AI which talks about only extracting patterns from data. Whereas AI can also use what is called as deductive reasoning. When you have a lot of facts and rules, you can dynamically derive knowledge from existing rules and facts. So there is a lot of AI which is without machine learning. And a lot of machine learning is possible without deep learning. Like, for example, I'm sure you have gone through algorithms like linear regression, logistic regression. And there are a lot of scenarios where you don't have sufficient data. So there you have to use machine learning. You cannot use deep learning. So both are myths that AI is not possible without machine learning. AI is very much possible without machine learning. Last 60 years, we have done that. Only now we have this machine learning suddenly become popular, but we have had expert systems. We have had AI-based optimization techniques for doing airline ticket optimization. A lot of examples of AI without machine learning. Machine learning has been successful in the past with SVM, with technologies like SVM, with linear regression, even face recognition without any deep learning. But deep learning, what it has done is it has made the task of working with unstructured data, images, text, etc., much more popular because of this avoiding of feature engineering. Okay, so let's proceed. When I say deep learning is about the automated feature extraction, we saw hierarchy of features. But what exactly are the hierarchy of features? What it is basically what is called as a MIMO architecture known as neural network. What is a neural network? Neural network is nothing but a multi-input, multi-output system where you have a basic input layer, then you have a output could be a class or it could be a simple value. And what in deep learning we do is we try to simulate the human biological neuron. If you see the structure, it's very similar. The way the neural network works is it basically has one input layer where it gets the input data and one output layer, and in between there can be multiple hidden layers. While neural network as a concept has been there 1956 onwards, but it's only in the recent past that because of the large structure of the networks which have successfully handled automatically extraction of features from images, etc., we see that today's deep learning architectures are having many layers and are successful at image processing, text processing, etc. So you see, what is exactly a neuron? A neuron actually is a simple mathematical combination like this. It's called as a single layer perceptron. What it does, it has input data where x1, x2, x3 come in, and each connection to the next layer has a weight. So if you have a node which has incoming nodes from previous layer, it has weight on each of the edge. And depending on the inputs x1, x2, xn, etc., you do a combination sigma wix. Then at the node, you perform a function known as thresholding. Is it greater than some level or less than some level? If it's greater than or equal to some level, you'll give output 1. If it is less than that, you'll give output 0. This was the first neural network which was built. Very simple idea. Sum of weight times input at all edges. Take that and see if it is greater than some threshold. If it is, yes. But this gave the power to what is called as really bringing some kind of a semblance of nonlinearity. But at the same time, it also brought some limitation. This kind of a function was very good at capturing a lot of conventional operators. For example, if you look at AND operator, you could find W1, W2, and W0 such that sigma of X and Y and 1, whatever you do, subject to the threshold function, you will behave like an AND function. So what happened is people started seeing that there's a lot of benefit in using the neural network phenomena of perceptron, which is this kind of a function, right, to model a lot of real functions. Example you saw is AND here, right? So here, if you see x plus y minus 2, you take 0, 0. You see 0, 0 minus 2. That means it is less than 0. So it is giving you 0. If you take and 1, 0, it gives minus 1. It's less than 0. It gives 0. If you take 1, 1, 1, 1, 2 minus 2, it gives 0. 0 is greater than equal to 0. So it gives you 1. For all others, it gives 0. So it is mimicking the AND function. Same thing you try for OR, you can also find similar way of manipulating and representing the neural network to represent the OR function. But the problem happened is when people try to capture XOR, this neural network could not capture the XOR function. Why? The reason is, if you see from a mapping of the functions and or XOR, you will typically see that the way the ones and zeros occur in AND and OR are such that you can draw a line to divide between 0 and 1. And that is why it is possible to model AND and OR using the single layer perceptron. Whereas if you look at XOR, XOR talks about basically it is not possible to have a single line separate ones and zeros. Try that. Any of you try that? You look at the graph of XOR. You think you can get one straight line to separate ones and zeros? Try if it's possible. Anyway, I'll give you 1 or 2 minutes. Try seeing if it's possible to have one straight line to separate zeros and ones in XOR. Do you think it's possible?
Nothing, sir. Not possible.
Possible. And that exactly what caused the problem of saying that XOR cannot be separated using a single straight line. Hence, it cannot be classified using a single layer perceptron. And this led to a large gap in pursuing the neural networks idea. Huge, about a couple of decades, people just didn't have interest in pursuing neural networks anymore, including Marvin Minsky wrote that, oh, these are not so important anymore. So it led to an AI winter. But later, some researchers started looking at, can we change the model by saying that if you see the diagram, sorry, one line may not be able to separate, but if you draw 2 lines after each one, you can separate ones and zeros, right? So what they said is, instead of a single layer perceptron, let's start with multiple layer perceptron, where you start from input, take one layer of neurons, then again one more layer, and then go forward. And that's how the logjam of AI winter was slowly removed by saying that let us start working with multiple layer perceptrons, where you have multiple hidden layers between the input and output. That gave rise to the modern day neural networks and the foundation of deep learning. So if you see, what typically happens in multi-layer perceptron is that start from input layer, then you compute this forward function, which is, as we saw, right, sigma of wxi, then you compute something based on a threshold function. You get the output, that becomes input for next layer. Then again, next layer compute, then you'll go to the next layer. Like that, you go all the way to the output layer. So at the output layer, as a result of the forward pass, you will get a certain value after having computed series of such transformations. But when people started saying multi-layer perceptrons are good because they can handle more complex functions, the big problem was also further expanded by saying that I don't need only a threshold function to be my nonlinear activation. I can have several kinds of activation function which can function on the output sigma wxi. So what are those activation functions? In the first case, when we started with single perceptron, it was a threshold function, right? Greater than some threshold, you get 1, less than threshold, you give 0. But now, once we talked about activation functions, we started seeing more and more nonlinear functions appearing in the horizon. So more and more complex neural networks started to get built by introducing an activation function called as sigmoid function. The sigmoid function typically is a very interesting property. Less than 0, it is usually 0. And as you go forward in the positive, it reaches 1. So most of the time, it's either 0 or 1 with a sharp jump between 0 and 1. That's how the sigmoid activation function is. Similarly, you can have other activation functions like tan hyperbolic. What hyperbolic function does is, for less than 0, it is minus 1. For above 0 of x, it's mostly 1. So it again is a sharp transition between minus 1 and 1. So it's an extension of the logistic or sigmoid activation function. Then you have another interesting activation function called ReLU, which is very useful, especially in image processing and CNN architecture. What ReLU does is it says, okay, ReLU of any argument is max of 0 and x. So what max of 0 and x gives you is 0 for all less than 0 and linear for all above 0. There is another function called a sin x. What it does is, if x is less than 0, it is minus 1. If x is greater than 0, it is plus 1. So if you see here, what we're doing is we are actually talking about several nonlinear activation functions. So what happens in the forward pass? You start from input layer, you start computing based on activation function applying on sigma wxi. You go all the way from input node all the way to the output node. So in the output node, you will get some value at the end, right? After having computed all the sigma wxi's applied activation function on it. But then whatever is the output value you get, do you think it's going to be the same as what you expect? Not. And that is where what you do in deep learning is you compute the error between expected output value at the output node and what you got, and that's called delta. And what you actually do in the next step is you do what is known as backpropagation. What is backpropagation? Initially, when you create the network, you assign random weights to all the edges. Based on that, you compute the forward step, right? Basically, forward step is sigma wxi applied with activation function. You compute next node, like that. But now, when you have found that there is a delta difference between actual and the final output at the output node, what you need to do is you need to propagate the errors from the output layer back to the previous layers, and you update the weights. And that is exactly what happens in backpropagation. So what backpropagation does is it recomputes the weights of the previous layer by looking at the delta at the output layer and doing a backward propagation step so that the output layer W is updated with something known as delta W. And how do you find the delta W? By looking at the error, whatever you got as delta, right? And taking the partial derivative of that with respect to each of the weight. This is exactly what happens in linear regression, in neural network. Let's not go deeper into the mathematics of gradient descent, but think of it like at each step, I'm propagating the error back to update the weights of the previous layer. And whatever change has happened to the delta W, that I'm passing to the next layer to update the weights. Like that, you keep doing all the way to the input node. and that is called as the back propagation step. And this is basically based on the idea of moving in the direction of maximum slope. So at the end of it, we see that the previous layer delta will be updated with a delta W. And whatever delta W happened here, that becomes the delta as input for next layer, which again can be differentiated and brought to the next layer. So like that, you keep on going all the way up to the weights of the edges connecting input layer to the first layer. So that one passes over. So one forward, one backward. But then what happens is, it is not that for every input data, you run the forward step and then you do the backward propagation for every input data. That becomes very costly. So what people usually do is they use batch. Batch means you compute all the forward steps for all the input data. Then you compute the average error across the entire input data as one batch. And then once you update in the back propagation the weights, then again, this is called one epoch. Then you run again one more batch through the entire input data, compute the average error, and then do one back propagation. That is one method called batch gradient descent. If you don't want to do across the whole batch, you can try to say the batch is divided into 10 mini batches. That means once you have 1/10 of the mini batch, you take the average error, update, back propagate. Again, second, like that. You do 10 times in one batch. That is called mini batch. But there is one more approach where you say that instead of running this over the across batch, you take a random input sample, run the forward, and then run the backward step. That's called stochastic gradient descent approach. So there are different ways by which each of them have their own merits and demerits. But at the end of the day, you have a stable neural network with stabilized weights, which are not going to change much. And that is when you output the whole network saying that this is my final classifier, or this is my final model, which is captured all the data in the input. That's exactly what happens in any deep learning model. So what you need to look at is, what are the things you want to vary here? The things you want to vary here are the architecture, how many layers, how many nodes in each. You may want to vary activation function. What is it you want? You want sigmoid, you want tan hyperbolic, you want different kinds of other activation functions. So those become your tools to work with when you want to apply deep learning based multi-layer perceptron on any particular data. Okay, so basically what I wanted to cover was what is the inside of what happens in this multi-layer deep learning approach. The features which is said, right? Automatically extraction of features. They're nothing but each node in the hierarchy of layers becomes a kind of a feature. So what we say is all the hidden layers become the feature layers. And the weights which are connecting to them are ultimately going to change and reach a stable state after having gone through several batches or several mini batches. So this is how actually deep learning works, in form of neural network at the core and taking data directly from images and extracting weights and creating the nodes, intermediate nodes, and ultimately leading to a network which has stable weights, which can classify any image which is given to it. Okay. So having said this, let me run one sample example, which will give you an idea of how this works. Okay, so this is how a typical program looks. This is a machine learning program using conventional Python scikit-learn library. We have a data here, which is basically a classification data. What this does is it has 4 columns. One is called admit, whether somebody is going to get a US admission based on 3 input arguments, GRE, GPA, and rank. Okay, so if you see the output, it can either be 0 or 1. This is the way the classifier program is. Now we have to develop a classifier for this. So what we will do is, we will take the data. Input data is GPA, GRE, and rank. Output is admit column. And I'll try to create a standard training test split. Now, here is what I want you to observe. I'm trying to create a neural network which has, let's say, 4 layers. 10 in first, second 10, third 20, next 22. And then activation function, I'm saying, is the sigmoid function. It's called logistic. And I'm trying to fit it. And I'll try to look at accuracy. It gives me 75% accuracy. Okay. So same thing, what I can change? I can now change the activation function. Let's say I want to use tan hyperbolic. Not changing that much. So suppose I want to change the architecture. Let's say I want to go with only hidden layers. First has 10, next has 10, next has 22. So I'm changing the architecture. Still not changing much. So 2 main controls you have is the structure of the neural network. Okay. And then you have the activation function. Suppose I want to, instead of all of this, I want to use the other one, ReLU. So let's say ReLU is the other activation function I've used. So it's not changing much, but the point is, these are the hyperparameters which you have when you're trying to apply a neural network for your classification problem. What are the neural network parameters? The structure of the neural network. You may decide to have more layers. Let's say I want to have 24 and then 44. Let's say 5 layers I want. That I can create and try to change. So what is happening is, it's not making much difference to the actual accuracy. So the typical hyperparameters when you are programming with neural networks based multi-layer perceptron is things like activation function, then structure of the neural network itself between the input and output layer. But what you're doing is actually a machine learning problem of classification. What's the classification? Here we're talking about, given a GRE, GPA, and rank, you want to see if a particular student will be admitted or not admitted to a US university. So given this kind of an application of deep learning for classification, I want to clearly stress out one thing. While we're using a neural network based deep learning architecture, but it is still doing the machine learning problem of classification. But the way it is doing is, it is using a structure which is based on neural network. There can be other applications, like you may want to use deep learning for image classification, which is what we'll show in the next session, where we will use a slightly different network called as convolutional neural network for image classification. But deep learning itself can be used for a typical classification approach. So what I want to do is, I want to then go to spend a couple of minutes in what are the application areas where deep learning is coming. Huge applications in image classification, fraud detection, video segmentation, object detection, spam analysis, intelligent chatbots, speech processing, driverless cars, etc. In cybersecurity, text summarization, video content extraction, intelligent robotic automation, business process improvement, customer segmentation, etc. So all these are actually pointing out to new kinds of possibilities of using deep learning, especially leveraging unstructured data. Okay. So basically, this is a very hurried coverage of the overall area of basic deep learning based on the conventional neural network idea. And the idea here is that we want to get away from artificially engineering features to more automatically extracting data from raw images, etc., which we will see very easily in the next session when we go through CNN-based architecture. So I hope this session, I think we're reaching some break time, but I'll take 5 minutes of questions before proceeding for break. Then we will do CNN in the next session. Any questions? There's no concept of max hidden layers because today I heard Google is working on some architectures with 500 layer Google Net. So there's huge architectures being prepared with large number of layers. Any other questions? Thank you. See, one thing I would like to be careful about the conventional approaches versus DL. See, DL will be useful when you really have a lot of raw data on which they are trained. So in terms of biometrics versus DL, if you have sufficient number of data which has captured different variations of whatever you're capturing, either fingerprint or iris or maybe human face, then it's okay. It's a good way of using. Regarding tumors classification, again, as I said, one of the domains where we'll be very careful about analyzing deep learning is the fact that we don't know if characteristics of one kind of tumor applies to everything else. So we need to be careful about what are the domain specific data which you can use to train the network. That's very important because it is, after all, playing with human health. So I'd be very careful when I will try to say that I will apply deep learning in actual medical use cases. I will be very careful about working with lots of domain specific training data used to train that. What did we do till now? See, DL is nothing but neural network. What is deep learning? All of this is only deep learning, right? So what did we say? We said that this is a statement I've made here. Basic building block of deep learning is neural network. There's nothing else. Today, there are different other architectures coming up like deep Boltzmann machine, deep Bayesian networks, but unless otherwise specified, deep learning is nothing but neural network. Current research area in DL, federated learning, try federated learning, try areas like CME's networks, deep Boltzmann machines, deep Bayesian networks. These are new areas. medical problems while working with original data. Small data sets are available, so it's very difficult. I don't think you should work with deep learning unless you have large data sets. Small data sets better to do with conventional machine learning. Use SVM. Be very careful that if you are using deep learning on small data, you'll get very inaccurate results. You may get 40% accuracy. Any other question? Any other questions? Sir, for stock price forecast, the whether real implement supervised or unsupervised, it doesn't matter. In the current example which I gave you, it was a supervised because it was doing a classification. But I can also use deep learning for clustering. So deep learning doesn't matter whether you use for clustering or for classification. Ultimately, idea is video segmentation. There are newer kinds of networks and pre-trained networks coming up like YOLO, etc. You should use them. Stock price forecast, we will work with LSTM, which we will talk in the afternoon. So just sending you a link of YouTube channel. You can all subscribe. It has all the detailed videos on different kinds of deep learning, different kinds of machine learning, etc. It would be great if all of you can subscribe to it and learn from there, because it's not just about this talk. If you want to refer to material beyond this, all of these talks are there as part of that. So in that channel, we have all the videos related to deep learning, machine learning. Any other question? Otherwise, we can take the break, which is supposed to be 15 minutes, and come back by 11:35.
Sir, we will start by 11:35, sir.
11:35 is okay?
Okay, sir. Okay. Right, sir.
So how to select activation function? Typically, this is again a part of the data scientist role. They will try different algorithms. Try with sigmoid, they will try with ReLU, see which one fits better accuracy.
So all the participants is joined by 11:35. Okay.
So overfitting, underfitting. Overfitting means if you change the training data, it will give a different accuracy. It will fail. Underfitting means accuracies are very small. You're not able to abstract actual patterns in the data. Overfitting means you're overfitting to that training data. You change the training data, your pattern changes. Underfitting means you're not even able to extract generality in the patterns. Okay, so let's meet at 11:35 and continue with our journey with exploration of more deep learning networks. Okay. For all of you who are interested, please go ahead and subscribe to this channel, which I have given.